Welcome to today's lecture. Let me remind you that we have been discussing the solar system, and in the last lecture we have seen that the solar system, the sun is the largest object in the solar system, and we have the 8 planets, and then we discussed the orbital parameters of these planets. We know that the planets move in ellipses around the sun. So, we discussed the orbital parameters, and we saw that they move in nearly circular orbits, and they are more or less coplanar to Earth's orbit around the sun. Then we saw the masses. We saw that the 4 inner planets, Mercury, Venus, Earth and Mars, these are relatively small, light, whereas the 4 outer planets, Jupiter, Saturn, Uranus and Neptune, they are relatively bigger and they are giants compared to the 4 inner planets. Having discussed this, we looked at the rotation of the planets, and we found that the rotation for nearly all the planets are aligned, and with the revolution, the orientation of the revolution. So, this can be explained in terms of the formation of the solar system, and it is now believed that the solar system formed from the collapse of a rotating gravitational collapse of a rotating spherical disk or spherical cloud of gas and dust, and this collapsed to form a rotating disk, which then fragmented to give the planets that we now see. And then I told you that we have these asteroids and comets instead of stars, and finally, we looked at the outer solar, so the distant solar system, and we discussed why Pluto is no longer a planet. Pluto is a dwarf planet. In today's lecture, we shall start our discussion by first taking up asteroids. So, asteroids are small rocky objects in orbit around the sun, and they could be as small as a few hundred meters, and the largest of these objects is 948 meters Ceres. And the asteroids include a large number of objects which are in orbit between Mars and Jupiter. This is referred to as the main belt of asteroids. Okay. In addition to this, we also have the near Earth asteroids. These are asteroids whose orbits approach the orbit of Earth, or sometimes they also cross the orbit of Earth. So, near Earth asteroids are of great concern for the sustenance of life on Earth, because the a collision with a large asteroid could have disastrous impact on Earth's atmosphere, and it could prove extremely hazardous for the sustenance of life on Earth. So, this picture shows you the main belt of asteroids, and this belt is located between the orbit of Mars and the orbit of Jupiter. Remember that the orbit of Mars, the outermost of the inner planets, is at 1.5 astronomical units. So, Mars is at 1.5 AU, and Jupiter, which is the one of the innermost of the outer planets, this is at 5 AU. So, we have this region spanning 3.5 astronomical units in radius, which is the place where you have the main asteroid belt. So, this is where the main asteroid belt is located. Every yellow object here is an asteroid. So, these are rocky objects whose size could vary from a few meters to a few hundred up to 1,000 kilometers, okay, 100 meters to 1,000 kilometers, and these are asteroids. So, they are all in orbit around the sun and they follow Kepler's laws. They are all in roughly circular orbit and they follow Kepler's laws. Now, you also have, in addition to these, you also have asteroids which are referred to as Trojans. So, these are asteroids which are bodies that are captured in Jupiter's 4th and 5th Lagrange points. So, let me explain this point in a little more detail. So, Lagrange considered this very interesting problem. The problem is as follows: you have a massive object like the sun and there is another object. So, in this case it is Jupiter. So, we considered the system made up of sun and Jupiter, and Jupiter we know is in a nearly circular orbit around the sun. So, you go to a reference frame which is rotating with Jupiter around the sun. So, this suppose you go to a reference frame which is rotating with Jupiter and then ask the question, are there positions where if I put a test particle it will be in equilibrium. Okay. So, let me repeat this. So, if I have two bodies in so like sun and Jupiter we know goes around the sun in a nearly circular orbit. So, Lagrange asked the question, suppose I go to a frame of reference which is co-rotating with Jupiter. So, in that reference frame Jupiter's position remains fixed. The sun obviously is fixed because that is where you have the origin. Now, the question is, are there positions where if I place a test particle it will be in equilibrium? And Lagrange found that there are 5 such points shown over here. These are referred to as L1, L2, L3, L4 and L5. So, these are the 5 Lagrange points and these are all positions where if I place a test particle which is also rotating with Jupiter. So, the test particle is in the same is rotating co-rotating with Jupiter, and if I place test particles in these any of these 5 positions it will be in equilibrium, it will not experience any force. But then he found that these are not points of stable equilibrium. L1, L2 and L3 are unstable equilibrium. So, even though I have a particle here in equilibrium, a small disturbance will move it away and it will never come back to the same equilibrium again. So, these are unstable equilibrium, but L4 and L5 are stable positions of stable equilibria. So, if I put a test particle here and if that test particle is co-rotating with Jupiter, it will remain there. So, these are points of stable equilibrium, and we find that there are objects which have been captured in Jupiter's 4th and 5th Lagrange points, and these objects are also these are asteroids, rocky objects which have been captured there, and these asteroids are referred to as Trojans. So, if you go back to the picture, you will see that in addition to this ring between Jupiter and Mars, you also find a profusion of asteroids here and here, and these asteroids being in circular orbit are co-rotating with Jupiter, and these are the 4th and 5th Lagrange points of the Sun Jupiter system. So, these asteroids have been captured here, they are in stable equilibrium and they co-rotate with Jupiter. Okay, so, these are the Trojan asteroids, very interesting kind of systems. Then you also have another class of asteroids which are called centaurs. These are in orbit between Jupiter and Neptune. And then we also have asteroids which are beyond Neptune. So, these are called trans-Neptunian objects, and we shall come back to this point later. And these are called also minor planets, and there is a whole class of objects which are there beyond Neptune. So, these also fall under the classification of asteroids. Okay. So, we have just discussed asteroids. These are rocky objects in orbit around the sun. Now, let us take up another very fascinating kind of object in the solar system. These are comets, and they are really spectacular objects that occasionally appear in the sky. So, what are these comets? These comets are essentially small icy bodies. So, they are frozen water and dust, and they are typically a few kilometers in extent, and these are objects that have formed in the outer solar system where it is extremely cold. So, you have these objects forming in the outer solar system, and they are essentially icy objects, frozen gases and water, and the orbit of these objects are, so they are there in the outer solar system, and if it happens that the orbit gets disturbed by a massive planet, and they may happen to come into the inner parts of the solar system, and they approach the sun to within 1 astronomical unit or less, and then when they approach the sun, they get heated up, and the content of these objects, it gets vaporized, and once it gets vaporized, then you have an atmosphere around these objects. So, you have a head of the comet which is the solid, which is still in the solid state, and there is a tail which is formed. So, and these that is the atmosphere, and these atmospheres could extend up to a few 100,000 kilometers. Okay. And we see it as a very spectacular object in the sky, this extended tail. So, the atmosphere of the comet is what gives it the name coma. It is a hazy kind of atmosphere around the comet, behind the head of the comet, and it glows. We see it because of reflected sunlight. Also, so there are dust particles and ice pieces there possibly which reflect the sunlight. In addition to this, the atmosphere has gases which have fluorescence. So, what is fluorescence? So, consider the gas making in the atmosphere. So, suppose it gets excited, the electron in this gas, in the molecule of the gas, gets excited to some state by, let us say, the ultraviolet or radiation from the sun, ultraviolet or visible radiation from the sun, and then it de-excites through some intermediate state, and this radiation comes out in the optical or visual, in the visual band. So, we could consider a situation where there is ultraviolet light impinging on the gas in the atmosphere of the comet, and that causes excitations which, so the ultraviolet light is not visible to us, but when it de-excites, it produces visible radiation, and this also causes the comet to glow. So, the comet is surrounded by a hazy glowing gas, and this is the tail of the comet, and the tail points away from the sun. Now, why does the tail of the comet point away from the sun? So, there are essentially two reasons which are shown over here. The gas is pushed out by the solar wind. So, this is the sun, and the sun, we know, is constantly emitting out a stream of ionized gas, plasma, which is called the solar wind. And if this is the comet, the vaporized gas from the comet is constantly being pushed outwards away from the sun by the solar wind. Further, the dust in the atmosphere experiences radiation pressure. So, we know that the radiation from the sun is carrying momentum, the momentum being h nu by c, each photon carries this much momentum. So, when these photons are absorbed by the dust in the atmosphere of the comet, they experience an outward push, and these two things together cause the tail to point away from the sun. So, the comets have a tail which points away from the sun. So, this is a picture of comet Halley, one of the most famous comets that we have. When it appears in the sky, it is quite spectacular, and it appears every 76 years. It has a period of 76 years. So, it is in orbit around the sun with a 76-year period, and it is not precisely 76 years, and the period is not constant. There are variations in the period due to the influence of other the gravitational influence of the other planets, etc. And the Halley comet, we now know, is in an orbit that has an eccentricity which is 0.967. So, roughly 0.97. So, it is a highly eccentric orbit. So, Halley comet is in orbit around the sun in an highly eccentric orbit with an eccentricity of 0.97 approximately. Let us take a look at the eccentricity of the other planets, just to remind ourselves. The other planets we have seen have extremely low eccentricities. Most of them have eccentricities which are in the second decimal place. Mercury is the planet with the most eccentric orbit, and it is 0.2, whereas all the other planets have eccentricities which are in the second decimal place. So, they are in nearly circular orbit. In contrast, the comet Halley and all comets typically can be in highly eccentric orbits. The semi-major axis is 17.8, so it is roughly around 18 astronomical units. So, it is well within the orbit of Uranus and possibly also let us just take a look. So, this is semi-major axis, it is well within the orbit of Uranus and not within, but the semi-major axis is smaller than that of Uranus and Neptune, but it is larger than that of Saturn. Now, let us ask the question, what is the nearest distance that this comet approaches the sun? So, we know that these comets are governed, the motion of the comets will also be governed by Kepler's laws, and so it moves in an ellipse, and the nearest distance, the distance of nearest approach is going to be the semi-major axis into 1 minus the eccentricity. So, it is 17 AU, roughly let us say 18 AU into into 0.03. So, it is 0.54 AU, which is just outside the Mercury. It is within the orbit of Venus, but does not cross the orbit of Mercury. It cuts the orbit of Venus and goes in, but not the orbit of Mercury. So, this is, it gets very close to the sun in this elliptic orbit, and let us also ask the question, what is the furthest distance? So, the furthest distance is the semi-major axis into 1 plus e, and this is approximately around 17 or 18 into 2. So, it is around 35 or 36 AU, which is beyond the orbit of Neptune, the furthest planet. Okay. So, let us just take a look at this. So, here this shows you the orbit of the comet Halley, and you can see that it approaches very close to the center, but it does not cut the orbit of Mercury, it goes quite close to it, and here you see it goes further away than the orbit of Neptune. So, it has a highly eccentric orbit which spans nearly the entire solar system. This let me show you the orbit of another comet. This comet is called Hale-Bopp, and it appeared in the sky in 1997. And this comet is estimated to have a time period of 2520 years, a tremendously long time period. And here you can see the orbit. It is a highly eccentric orbit which goes way beyond the known parts of the solar system. So, this is another comet which was very spectacular when it appeared in the sky in 1997, and it will appear next around 2000 years, 2,500 years from now. So, comets we see are roughly can be classified into two kinds, and we have seen examples of both these kinds of comets. So, we have the short period comets. These are of period less than 200 years. Example, the comet Halley, which we just saw and discussed, whose picture we just saw. And these comets are quite often in the ecliptic plane. So, they have orbits which are quite often close to the orbit of the Earth and the other planets around the Sun. And you can see it here for Halley also. The orbit of Halley is not very far away from the orbit from the plane in which the Earth and the other planets move around the Sun, not very far away. Well, it is inclined, but not very inclined. Okay. And there are short period comets which have periods in the range 5 to 7 years, and such comets frequently pass close to the Sun, and these frequent passes close to the Sun completely vaporize these comets, and they are not very spectacular because they lose their material pretty fast, and they do not last for a very long time either. But Halley's comet we know has a period of 76 years. So, it will go through the several orbits before it is completely vaporized. Okay. So, these are the short period comets. You also have long period comets whose ages could vary between 200 years to a million years. So, we just saw an example, the Hale-Bopp comet, which has a period of 2500 years. And these are often and typically are off the ecliptic. So, let us look at this picture again. This is Hale-Bopp, and you see it is practically orthogonal to the plane of the ecliptic. Okay. So, we see that there are two kinds of comets, the short period comets and the long period comets. So, now let us ask the question, where do these comets come from? Well, we believe that the objects that make up the comet were formed when the solar system was formed at the same time. Asteroids and comets, both of these are objects were, we believe, all formed at the same time at which the solar system was formed. But a part of the matter that fragmented when the disk that formed the solar system fragmented was assimilated into planets. But some other parts did not get assimilated into planets, and they are still hanging around in the solar system in the form of rocks and icy objects, and these are what we see as asteroids, and if they come close to the Sun, they become comets. Okay. So, that is the basic picture, but so question is, but why do they suddenly come close to the Sun? What is their origin? They have not moving in these highly eccentric orbits which approach the Sun for a very long time, not for 4.5 billion years, which is the age of the Sun. So, there has been some recent event in the past which has brought them into an orbit which approaches the Sun, and they become comets. So, the question is, where do they come from? So, the origin is believed that the long period and the short period comets have different origins. So, the long period comets and the short period comets, they are both in bound orbits around the sun, and the long period comets, it is found, have aphelion, that is the distance of furthest distance from the sun. So, they are in bound orbits which are ellipses which follow Kepler's laws, and the furthest distance from the sun in these ellipses could be as large as 50,000 astronomical units. That is what it is typically found. These are long periods. So, period is proportional to the semi major axis cube. So, if for long period comets you would expect them to have large semi major axis, and the furthest distance from the sun are found to be of the order of 50,000 AU. Further, they do not have any preferred direction. So, the furthest distance from the sun. So, if this is the sun, if you look at the direction of the orbits, they seem to be distributed equally in roughly all directions. There is no preferred direction. You find comets to be distributed roughly in all directions. So, question is, where do they come from? And we believe that they do not come from interstellar space, they originate somewhere within the solar system. So, this Dutch astronomer Oort, very famous Dutch astronomer who has contributed very significantly to astrophysics in the 20th century, Oort proposed that there is a cloud of objects at the periphery of the solar system. And so, this cloud of objects, he proposed, could be, the distances could be between 50,000 astronomical units to 150,000 astronomical units. This was a remarkable proposition because the solar system, as we know it, extends up to Neptune 50 astronomical units, and such a proposal pushes the extent of the solar system 1,000 times larger, 1,000, or this is 3,000 times larger. Okay. But that is what Oort proposed, that there is this cloud of objects which is now called the Oort cloud, and there could be as many as 1 trillion objects in that cloud. And so, these objects are there in orbit around the sun in the Oort cloud, they are orbiting the sun, and then maybe there is some disturbance from some passing star or from the some disturbance in the gravitational potential of the galactic disk caused a change in the orbit, and they may get the changed orbit may bring them, the disturbed orbit may bring them into the inner solar system, and such an object would then be seen as a long period comet. Okay, so, that was the picture proposed by Oort. So, he proposed that there is a cloud of such objects in space in the periphery of the solar system. Okay. Now, the question then arises, what is the source of Oort clouds? Okay. So, it is believed that there are asteroids. So, there are asteroids between in orbit between Uranus and Neptune, and it is now currently believed that these asteroids between Uranus and Neptune, so they happen to get disturbed by one of these massive planets, Uranus, Neptune or Saturn, and as a consequence of this disturbance. So, these asteroids are in circular orbit between Uranus and Neptune, and some passing planet causes a disturbance, and as a consequence of the disturbance, the asteroid gets scattered to outer parts of the solar system, and such scattered objects form the Oort cloud. That is the prevalent picture of how the Oort cloud was formed. So, asteroids between Uranus and Neptune are scattered, are disturbed, their orbits are disturbed by the massive planets, and they get scattered to the distant parts of the solar system, and they form the Oort cloud between 50,000 and 150,000 AU from the sun, and they remain there in some kind of circular orbits around the sun. Okay. So, that is the picture for the long period comets. So, long period comets are objects which were formed in the outer part of the solar system between Uranus and Neptune. They got scattered out to even further distances, 50,000 AU, 150,000 AU, where you have the Oort cloud, and then something disturbs them there and they come into this inner solar system and you see them as long period comets. Now, what about the short period comets? So, several scientists in the late 19th century and early 20th century, early and middle 20th century, they proposed that that there are objects, small objects in the solar system beyond Neptune's orbit, and these objects are called trans-Neptunian objects. Okay. And such objects in orbit around the sun beyond Neptune's orbit. So, they are there orbiting the sun, and some passing planet or some passing object disturbs them from the circular orbit, and the new orbit brings them close to the interior of the solar system, and these objects are then seen as short period comets. This was the picture which was proposed by several scientists, and here I show you the name of some of these scientists. Leonard, then you have in the early 20th century, you have Edgeworth, middle 20th century, and Kuiper. So, these objects beyond Neptune, trans-Neptunian objects, they are jointly referred to as the Edgeworth-Kuiper belt or the Kuiper belt. But at the time of this proposal, there were no known objects beyond Neptune. Well, Pluto was there, and that is all. There were no known asteroids beyond Neptune. Okay. So, this is so it was hypothesized that between 30 to 50 astronomical units from the sun, you have these objects hanging around in circular orbit around the sun, and these objects were referred to as the Edgeworth-Kuiper or the Kuiper belt, and these objects were postulated as the source for the short period comets. But you can imagine that detecting such objects, asteroids beyond Neptune, is an extremely difficult task. Why? Because these objects are going to be extremely faint, and because you are trying to detect an object a few kilometers large, maybe 100 or at most 1,000 kilometers large, located in orbit beyond Neptune. So, few kilometers large, located in orbit beyond Neptune, and the only reason why you would see them is because of the reflected sunlight. So, it is quite clear that such an object would be extremely faint on the sky, and further the entire sky is filled with a variety of objects, stars, okay, etc. So, how would you distinguish such an object, that how would you identify that this is an object located beyond Neptune, a rocky object or an icy object located an asteroid located beyond Neptune. So, this is an extremely difficult task, but the first such detection, the first Edgeworth-Kuiper belt object was detected in 1992 by Jubit and Lulu, and basically the technique which is used for such a detection is that of blinking. So, what is the basic idea there? The basic idea there is you take pictures of the sky, same part of the sky, on two different dates, significantly different dates, maybe a year apart or maybe more, and we know that the stars will maintain fixed positions, but any such asteroid will move on the sky, because it is near to us and we will see a discernible motion. So, it may appear here in one picture and it may appear in a different place in the other picture. Question is how to detect this. There are any picture of the sky will have a tremendous number of objects. How to distinguish which one of them has moved, and the motion is going to be extremely small. So, there is a technique of blinking. What you do is there is a device which will alternately show you both these pictures, and the object that has moved is going to move back and forth when you see these two pictures very in close succession. It is going to move back and forth between the two positions in these two plates, and your eye will automatically then pick it out. And this is the technique of blinking which has been used to identify such objects. And the first EKBO object, Edgeworth-Kuiper belt object, was identified by Jewett and Lulu in 1992. And after that, around 1000 Edgeworth-Kuiper belt objects are known, have been identified, and it is estimated that there are 70,000 objects larger than 100 kilometers in the Edgeworth-Kuiper belt. Okay, so, this was a tremendous revolution in our idea about the solar system. So, prior to this, our knowledge of the solar system extended only up to Neptune and Pluto. Pluto was then believed to be a planet, then classified as a planet, and that was the end of our solar system. So, around 30 astronomical units, and then there was suddenly a discovery of objects beyond Neptune, many objects beyond Neptune, and it is now estimated that there are 70,000 such objects of size greater than 100 kilometers. Okay. So, this was primarily the main reason why Pluto had to be declared not to be a planet, because it was found that there are many objects beyond Pluto, and some of these objects have masses comparable to Pluto, if not more. So, then the question is whether do we include all these objects as planets or what do we do. So, finally, it was the classification which I discussed in the last class was introduced, and Pluto was then removed from the list of planets. So, these objects which have been discovered beyond Neptune, they are mainly ice. So, they are frozen volatiles, frozen methane, ammonia and water and other volatile substances. The temperature in these parts is 50 Kelvin, outer solar system extremely cold, where all of these things are frozen, and Pluto is the largest known Edgeworth-Kuiper belt object. So, these are objects beyond Neptune. So, Pluto is now is classified as being part of the Edgeworth-Kuiper belt, and in addition to Pluto you have several other objects here, dwarf planets like Makemake, Haumea, etc. So, let me show you a picture. This picture shows you the outer solar system. The inner asteroid belt can be seen here within the orbit of Jupiter, and then you have Saturn, Uranus and Neptune. So, this is Neptune at around 30 astronomical units, and beyond this you see there are all these asteroids. This is the Kuiper belt, Kuiper Edgeworth belt, and Pluto is a part of this Kuiper Edgeworth belt. Okay. So, this is the outer solar system and this is the Edgeworth-Kuiper belt. You have all of these objects over here, asteroids. So, in addition to the main belt over here between Mars and Jupiter, you also have an asteroid belt over here, which is the Kuiper Edgeworth belt. But now it is believed that the Kuiper belt is possibly not the source of short period comets, and it is believed that the short period comets could originate in what is called the scattered disk. So, the scattered disk is the part of the solar system which is beyond 50 astronomical units. So, let me show you a picture of this, what we believe is the scattered solar disk, scattered disk. So, this picture, now the scale has become enormously large. Recollect that Neptune is the furthest planet, and beyond Neptune you have the Edgeworth-Kuiper belt, which is very prominent over here, and now you have all of these dwarf planets. Let us just look at them. So, you have Sedna over here, you have Eris over here, and then you have Makemake and Haumea and Pluto. Pluto is quite inside over here, okay, and these are also other dwarf planets, and they extend much beyond the Edgeworth-Kuiper belt, and this is possibly where you have the scattered disk. So, what we learned just now is that our picture of the solar system is now revolutionized. We had earlier the solar system was limited to Neptune and Pluto within few tens of astronomical units, 30 astronomical units, but then it got extended to the Kuiper belt up to 50 astronomical units, and now we believe that there is a scattered disk beyond. Let us go back and ask the question, what is the mass of the solar system? How has these new discoveries, how have these changed our idea about the mass of the solar system? It is now estimated that the Kuiper belt contains between 10 to the power 8 and 10 to the power 10 objects greater than size in 1 kilometer, and the Oort cloud contains objects 10 to the power 12 to 10 to the power 14 objects of size greater than 1 kilometer. Now, the total mass contribution from these objects, the estimates vary, but if you take the upper end of these estimates, then the mass in these objects exceeds the mass in the planets, the known mass in the planets. So, this is the table which I showed you right in the beginning of our discussion of the solar system. The sun contains the largest fraction, and then you have the planets, and the other objects here have 1/10 roughly of what the mass in the planets. But if these estimates are correct, then the mass distribution between the planets and these other objects is going to get reversed. Okay. So, let me end our discussion of the solar system by telling you that the outer solar system, the Kuiper belt and beyond, still remains to be explored, and the outer parts of the solar system is the frontier is one of the frontier areas in the exploration of the solar system. It still remains to be explored, and an exploration, the findings of such exploration may really change our notion of the constitution, the mass constitution of the solar system. We now believe that the planets contain the bulk of the mass outside the sun. This may get completely revolutionized, and it may turn out that the Oort cloud and the Kuiper belt and the scattered disk contain more mass than the planets. So, this is something which is still an open area to be studied, and more observations are required before we can really say something about this. So, that is the frontier area in our knowledge of the solar system. Okay, so, let me end our discussion of the solar system here, and in the next lecture we shall move on to some other topic.